Session, I'll be talking about different discrete probability distribution. Just giving you a brief overview of each of these distributions and how do you really use them in R. Right? If I really want to find out the probability function, how do I use it? If I want to find out cumulative distribution function, how do you use it? If I really want to find out the quantile corresponding to the value corresponding to a particular quantile, or if I want to generate some kind of random numbers associated with a particular distribution, how do I really use R to generate the data associated with each of these distributions? So we are going to take up the Bernoulli distribution, the binomial, geometric, hypergeometric, the Poisson distribution, negative binomial distribution, and finally we would just have a quick introduction to the Wilcoxon rank sum statistic, which would be used as an alternative to the t-test in our hypothesis testing sessions that we are going to look at later on. Now, generally, whether it is continuous or discrete, whatever are the distributions, in R, there are four set of functions. R is supporting four set of prefixes. So in some cases you can give a prefix as a D, in some cases it could be P, it could be Q, it could be R. So going with each one of them, if I am giving a prefix as P, it's like I am trying to find out the cumulative probability. So which is nothing but I will get the probability that X takes on values less than or equal to X. This is what is the P. So if I am talking about in the next slide, I'll quickly put up different kinds of distributions which the base R package is supporting. But the moment I put a P before that distribution, I'll get the cumulative probability distribution. Similarly, when I put a D, it is like a density function. In case of discrete variables, it's nothing but it is the probability of X is equal to X. That is what I can get through the usage of D. And when I'm using Q, probably take it as opposite of P. For what I will give probability as an input and it will compute this X as the output. So for what possible value of X, the probability of X less than or equal to X is equal to this much. That is what we are calling as the quantiles of the distribution. So probably you look at it as the inverse of the cumulative distribution, because the cumulative probability distribution will give me the probability of X less than or equal to X. But once I give the probability, it will the Q function will find out what is this value of X, where probability is of X less than or equal to X is that much. And when I want to randomly generate some kind of data set following a particular distribution, I'll prefix an R before it. So we'll try to use all these things as we move along in this session. So these are some set of functions which R supports, different kinds of distribution supported by R, but of course this table contains a mixture of both discrete as well as continuous distribution. So you find beta is a continuous, binom is a discrete, which we are going to take up in this session. Cauchy is continuous. So these things which are continuous, I'll deal in a session which is a separate session which is called as continuous probability distribution. So in this session on discrete, I'm only looking at the discrete session, discrete probability distributions itself. Yes, geometric is one discrete. Hypergeometric is a discrete. log normal, logistic, negative binomial is discrete, normal is continuous, Poisson is discrete, Wilcoxon sign rank is discrete, the T is continuous, uniform is continuous, right? Bible is continuous, Wilcox rank sum is discrete. So I can very well talk about these discrete functions, and for all these functions, as we have clearly indicated, as I am clearly telling you, all these four, probably if I want binomial distribution, when I say P binom, I will get probability, the binomial data is following a binomial distribution, I will get probability of x less than or equal to x. When I am using the d binom function, I will get probability of x equal to x. When I am using q binom as a function, I will give a probability, and based on that I will get that particular value of x where p of x less than or equal to x exists. And finally, when I am using R binom, I will be able to randomly generate numbers which are following a binomial distribution. So that's how you can prefix these PDQRs before each of these functions that are listed, which can give us the comfort level in terms of playing around with different kinds of distribution, right? Now, quickly looking at Bernoulli distribution. There's nothing much to talk about Bernoulli distribution because we are talking about one trial, right? We are doing an experiment once, and out of which there is a probability P where the success can occur. Success is what I am calling as 1, and the remaining probability 1 minus P where a failure can occur. Failure means 0. So there are only two possible outcomes, success or failure. Generally success is denoted with 1 and failure is denoted with a 0. So if I am trying to find out the distribution that is underlying this kind of a binary response, I am calling it as a Bernoulli distribution. So there is, if I am talking about probability of x, right? So when I'm saying P is the probability of occurrence of an event, I'm putting it as P to the power of x, and failure is 1 minus P to the power 1 minus x. Now x could be only either 0 or 1. So if x is 0, then it is P to the power of 0 into 1 minus P. So overall lies as 1 minus P, which is failure. So the probability of getting 0 successes is 1 minus P. Probability of getting 1 success, if I am putting it P to the power of 1 into 1 minus P to the power 0. So which will end up as P. So the probability of success is P, probability of failure is 1 minus P. And expectation, which is nothing but 0 into P plus 1 into 1 minus P. So which is working out, so when we are talking about x times, right? Okay, 0 is 0 successes, the probability is 1 minus P, and 1 success, the probability is P. Overall the expected value is P. Similarly, when you are talking of expected value of x squared, the same logic I can use, 0 squared times 1 minus P plus 1 squared times 1 minus 1 squared times P, which is again P. Expected value of x squared is also P. Expected value of x is also P. So variance is nothing but expected value of x squared minus expected value of x whole square. So which becomes P into 1 minus P. So that's how we compute these things. There is nothing much to do in R associated with these, because it's not too many times a particular experiment is repeated. The same Bernoulli distribution will actually pave way for us to understand the binomial distribution in depth. Right? The same experiment, instead of performing it once, if I perform it n number of times, right? The same. The probability of success is P, failure is 1 minus P, all else remaining the same. But if this experiment is performed instead of once, multiple number of times, that is where the Bernoulli distribution is giving rise to a binomial distribution. So it's when we are talking about a binomial distribution, still we are using the same context, p per x, 1 minus p to the power n 1 minus x. Instead of 1 minus x, we are talking of n minus x, because